Hi, welcome to week 2 of the Extreme Value Theory course. This week what we're going to consider is different ways that we can represent extreme values that lead to better statistical inference techniques. In chapter 3.1 of the notes, what we look at is how extreme values can be represented as a point process, and point processes are something that you might not be familiar with already. So this video is going to give you an introduction to the topic. So before we get into the new content, let's just roll back and start thinking about a Poisson distribution, something that you're likely to have encountered before. A Poisson random variable x with rate parameter lambda has the following probability mass function. So for values of x that are non-negative integers, the probability of x equaling that's lowercase x is given by lambda to the x multiplied by the exponent of minus lambda, all divided by x factorial. This is something that you've likely covered in previous courses, and when it was introduced to you, it might have been introduced as a good model for event counts. So one classic example is using it to model the number of rabbits observed in a field. So in this picture, we've got two fields, field A and field B, and NA is going to represent the number of events or the number of rabbits that we see on field A, while NB is going to represent the number of rabbits on field B. So in this case, we've got 2 rabbits in field A and 3 rabbits in field B. And what we're aware of as statistical modelers is that if we've gone at a different time to look at this field, then we might have seen a different number of rabbits in each field. So for example, we might have seen 4 rabbits in field A and none in field B. This Poisson random variable then gives us a way to describe the variability in that event count. So what we have is that the number of events on field A, NA, can be modeled as a Poisson random variable, where the rate of that random variable is going to scale with the area of the field. So lambda here is being multiplied by the modulus of A. And what that means is that if we're to double the size of the field, we're going to expect twice as many rabbits to be observed on average. And this lambda represents the number of rabbits that we're going to see per unit area of field A. And similarly, if the rabbit rate is the same in field B, NB could be modeled as a Poisson random variable with rate parameter lambda multiplied by the modulus of B. So what properties do these have? They give us a great model for event counts where the mean and the dispersion are equal. And if we have independent increments, so field A and field B don't overlap, and these two event counts we can assume to be independent. So what Poisson processes do is they extend this idea of using a Poisson random variable to model counts to also allow us to describe the locations of events within the observation regions. So the way in which they do this is they extend the idea of a rate parameter to be a rate or intensity function. What this is a function that goes from your observation region, in this case some subset of R2, to the non-negative real numbers. So it doesn't really make sense for events to occur at a negative rate. The number of events that you see on each region follows in very much the same way as what we saw before. So the event count on a set A is going to be Poisson distributed with the parameter capital lambda of A. And what this represents is the integral of the intensity over that region. So as we saw before, if we double the size of the region and this intensity is constant, then we're going to double the expected number of points. Given the number of events that we're going to observe on the region, the locations of these events are random, they're independent of one another, and they're determined to be, they're allocated proportional to the intensity function lambda of x and y. So where this intensity function is high, we're going to expect to see more of our points happening there. The independent increments property still holds. So if we've got disjoint sets A and B, then the event counts on each of these are going to be independent random variables. So let's look at a bit of an example of this to make it more concrete. Here, what we've got are two example point processes, and there are Poisson processes. So our total event count follows a Poisson distribution, and they're homogeneous, which means that the intensity function takes a constant value. In this case, we've got 3 realizations of each point process, given by each row of the picture here, where the 2 intensity functions are given by lambda of xy equals 3 and lambda of xy is equal to 6. So in this bottom row, we're expecting to see about twice as many points each time as in the top row. But note that between each realization of each process, we're getting a different number of events happening, and the locations of those events are also changing. We can extend this idea further to consider inhomogeneous Poisson processes, which is simply when the intensity function doesn't take a constant value. So in this case, I've defined the fields to be of unit area and to have the origin be specified as this bottom left-hand corner. And the intensity function for each process is now given by 3 times x plus y or 6 times x plus y. What this means is that we end up with the expected number of points remaining the same, but then in each realization, we're going to expect the points to be happening more towards the top right-hand corner and fewer points to be happening towards the bottom left-hand corner of the field. So let's look at this again and say, okay, if we've got an observed point pattern, which we're going to represent by a vector x of planar locations, and each of those planar locations is going to be on some set A. In the lecture notes, what we're going to look at is a very specific form for A, which is regions that look like 0, 1 by u to infinity. But this holds more generally. So if we have this observed point pattern and we've got a parametric form for lambda, where the parameters of that function are given by theta, then what we can do is use maximum likelihood to estimate what those parameters are, and in turn to estimate our intensity function lambda. So the likelihood for a Poisson process is going to be a function of the parameters of the intensity function given the observed data, which is simply the probability of the observed point pattern for a particular value of theta. So because our point pattern has 2 random aspects, the number of points and their locations, this is the probability of observing n events on A, and each of those events happening where we saw it happening. Conditional on the event count, the locations are independent, so this can be split up to be the probability that we see n events on A, probability that NA is equal to A, the probability that NA is equal to little n, and then the product over each of our observed events of the intensity at its location divided by the integrated intensity of the whole region. What this does is it normalizes our intensity function to turn it into a valid probability density function. So in the third line, all we're doing is substituting the Poisson PMF for this probability expression. And what we can see is that this capital lambda to the A of A to the N is going to cancel with the term in the product, so that our overall Poisson process likelihood is going to be proportional to the exponent of the negative integrated intensity multiplied by the product over all of our observed events of the intensity at that event location. And each of these 2 functions, lowercase and uppercase lambda, are going to be determined by our parameters theta. So what we can do is numerically maximize this over values of theta to get our MLE for theta, and therefore our estimate of what the intensity function is. This gives us a way of going from an observed point pattern to a fitted Poisson process model. And this is going to be useful when we start thinking of extreme values of the point process. The other concept that is useful when we're thinking about extreme values as a point process is the idea of point process convergence. So to think about this, we need to think about more than one point process, and in fact think about a sequence of point processes, which we'll describe here by P1, P2, and so on. If these sequence of point processes converges, then we're going to say that that converges to a limit point process P, and we can demonstrate that this happens in one of two ways. The first is to say that as we move through this sequence of point processes, the intensity functions, which we'll call lambda1 associated with point process 1, lambda2 associated with point process 2, and so on, that lambda1, lambda2, and so on converge to a limiting intensity function lambda as n goes to infinity. So, for example, if our nth intensity function is given by the sum from I equals 1 to n of 2 to the minus I, then as n goes to infinity, this is just going to converge to a homogeneous Poisson process with unit rate. The second way of doing this, and this one should be a 2 here, is to show that as n goes to infinity again, if we're looking at regions B that look like rectangles, then the counting measure, which is just the fancy word for that random variable n of B, satisfy two properties. We want the expected event count on A. Sorry, this A should be a B. So the expected event count on B in the nth point process converges to the expected event count in the limit process. We also want that the probability that there are no events on B converges to the limiting probability that there are no events on B. If we can show that these two properties hold, or that this property holds, then we've shown that the sequence of point processes converges to that limit point process as n goes to infinity. It's going to be a key result that we're going to rely on in the notes, and we're going to be using this second way of showing point process convergence. So that was quite a lot of information to take in all at once, and that's everything we need to know about point processes for this course. It's really barely scratched the surface of the things that you can do with point processes, and if this is something that's interested you, there's a whole lot more fun that you can have learning about point processes if that's something you're interested in. So your next activity from this is going to be to go on and self-study chapter 3.1 of the lecture notes, which goes on to look at how we can apply these ideas that we've just covered to an extreme value setting. Thank you very much for your time, and I'll see you in the next video.